All right, so this is section 1 in chapter 7, exploring exponential models. We've kind of been building up till here. Your whole retired life is an exponential model. All of your home loans, your car loans, your student loans are exponential models. So this is we've kind of been steamrolling, learning everything so we can get to this point. This is the for real in your life where things make a difference, actual use it place. So our learning objective is to model exponential growth and decay. We can represent repeated multiplication with a function of form y equals a b to the x. So I want you to highlight that. This is our foundational formula. Y equals a times b to the x. An exponential function is a function with the general form y equals a b to the x, with b greater than 0, b not equaling 1. An exponential function, the base b is a constant. The exponent x is the independent variable with the domain, the set of all real numbers. All right, so the first thing we're going to look at is the graph of an exponential function. So we have 3 that we're going to graph here. When we are graphing functions at this level, we are just going to make a table. Super easy to make a table. All right, so we're going to make a little XY table for this.
What the heck? They're square. Oh, what the heck? Whoa. What the
All right, so when you make a table, when I put in 0 for x, 4 to the 0 is 1. So when I plug in 0, I get 1. When I plug in 1, I get 4 to the 1, which is equal to 4. So over 1 up 4. So plot these points on your graph. When I plug in 2, I get 4 squared, which is 16. So over 2 up 16. And then when I plug in 3, oh my goodness gracious, it's 64. I'm kind of off my graph at that point. All right, let's do the same thing for the next guy. 1/3 to the x, so I'm going to plug in 0, 1, 2, 3, and 4. Anything to the 0 power is 1. One third to the 1 is 1/3. 1/3 squared is 1/9. So I got 1 over 1 up 1/3. Boop. Over 2 1/9. Oh, we're getting way low. Let's do let's work smarter, not harder. Okay, let this be y equals 1, y equals 2, and y equals 3. So at 0, we're 1. Over 1, we're up 1/3. Over 2, we're up 1/9. Over 3, we're up 1/27. And we just keep getting smaller and smaller from there. Phew, last one. XY table.
I grabbed it on our calculator. We have to.
Do an XY table?
No. Graph it on there.
Yes. Yep. So 0, 1, 2, 3, and 4. 3 to the 0 is 1. 1 times 2 is 2. 3 to the 1 is 3 times 2 is 6. 3 squared is 9. 2 times 9 is 18. 3 to the third is 27. 2 times 27 is 54. And then 3 to the fourth is 81. And 81 times 2 is 162. Alright, so I'm going to be able to graph all the way up till here, and then it's going to shoot right off on my graph. So, but let's get those points down. Over 0 up 2. Over 1 up 6. Over 2 up 18. And then I'm off my graph. All right, there are two types of exponential behavior. There's exponential growth and exponential decay. The way I remember it is growth grows, decay gets smaller. The x-axis is an asymptote because there is no value you can put in for x into a power that will produce a negative y value. For exponential growth, as the value of x increases, the value of y also increases. For exponential decay, the value of x increases and y decreases, and it actually approaches 0. The exponential functions here are asymptotic to the x-axis. An asymptote, this is new for us, definitely going to highlight it. An asymptote is a line that a graph approaches as x or y increases in absolute value. So if a is greater than 0, so if my value out front is greater than 0, let's see if I can get it. So if this value a is greater than 0 and b is greater than 1, then we have growth. The important part is the b part, because for both situations a is greater than 0. Okay, and if a is greater than 0 and b is in between 0 and 1, then we have decay. In either case, the y-intercept is 0, a. So whatever that a value is, that coefficient, that tells us what our y-intercept is. The domain is all real numbers, and the asymptote is y equals 0. The range is y greater than 0. All right, so now we're just going to look at these scenarios and determine if it's exponential growth or decay and what the y-intercept is. Okay, so for this first one, a is 3 and b is 4. Because b is greater than 1, it is a growth. The y-intercept is 0, a. Since a is 3, it would be 0, 3. The second one, because our b value is between 0 and 1, it's 0.75, we have a decay situation. Since the A value is 11, the y-intercept is 0, 11. All right, so let's take a look at C. C is the hard one. You put $2,000 into a college savings account for 4 years. The account pays 6% interest annually. So if I'm going to put this into y equals a b to the x, a is our y-intercept. It's our first value. So at time 0, how much money do we have? We start out with $2,000. B is what we're increasing by every year. And it is, we use 0.6 or 0.06 to find it. But what about taking in, that'll just give us the interest. I want to know how much money I have in there to begin with. So I have to start with 1. Because what's 1 times 2,000? So that puts that 2,000 into your bank account. Then we add on the interest. So that 0.06 takes your original amount and adds the 6% interest onto it. And then we have X is going to be our number of years. All right, so we have, do we have a growth or decay situation? We have a growth because our value is greater than 1, our B value. If we didn't include the 1 and forgot and just put 0.06, we'd be decaying. And that's not at all, when your money is decaying, that's when you have, that's a red alert. So, and then our intercept would be 0, 2,000 because I start out with $2,000. Booyah.
So that just feels like explanatory.
All right, so for exponential growth, y equals a b to the x with b greater than 1. B is called the growth factor. The percentage increase r, written as a decimal, is the rate of increase or the growth rate. Be sure to add 1 to your rate before you input it in for b in your function. If you don't, if you just put in, like I'm getting 50% back, and I just put in 0.5, that is technically a decay. And for decay, if your B value is between 0 and 1, then B is the decay factor. It also follows that the percentage decrease, R, is the rate of decay. Usually, the rate of decay is expressed as a negative quantity. So B equals 1 plus R. Okay. And then R would be less than 0. So if you're losing 15% of, we'll do it a good way. Say you weigh 400 pounds, and every month you lose 15% of your body. So then the losing or the decay rate would be minus 0.15. So 1 minus 0.15 would be 85%. Okay, so you can model exponential growth or decay with this function. A of t is equal to your initial amount times 1 plus r. If you're growing, r is positive. If you're decaying, r is negative. And then that's raised to the t power, where t is the number of time periods. For growth or decay to be exponential, a quantity changes by a fixed percentage each time period. So let's look at the money savings problem again. Suppose you invest $500 into a savings account that pays, so if you're getting paid, your money is going to grow, 3.5% annual interest. How much will the account be after 5 years? So we're going to take this function. And we're going to input our little pieces. So our initial amount is $500. Our rate is 3.5, so that's 0.035. And T is our time period. Our specific question asks, what is it after 5 years? So we're going to put in 5 for T. 0.035 to the 5th power. And all this is the calculator. So that's equal to $593.84. If we take this exact same problem, and because we haven't learned the necessary skills to undo this, we are going to find out using our graph when the account will contain at least $650. So my A of T is 650. My starting value is 500 plus times 1.035 to the T. So I'm going to graph y equals 650, and I'm going to graph y equals 500 times 1.035 T. We will learn later on in this chapter how to do this algebraically, but for now, here's how we do it using a calculator. All right, when you graph y equals 500 times 1.035 to the x and y equals 650, their intersection point is your solution. So, with inside year 7, you'll hit 650. So then you go back to the question. Please make sure you read the question carefully, because are they going to have you identify year 7 or year 8? So let's read what the question tells us. When will the account contain at least $650? So in year 7, right, almost a little beyond the middle, the account will have, well, not really, because we can only do, it'll have to be in year 8. Because when do they compound the interest? When does it happen? Does it happen in the middle of the year? No, it's at the end of each year. So we won't see that in our account until year 8 when they compound the interest. So it'll be year 8. So at $650, it's year 8. Okay, so like the previous problem, sometimes we have a discrete situation. Discrete is the opposite of continuous. Continuous is when we have the mid-year, the quarterly, the in-between values. A discrete situation says we are only taking points at certain times, and we're not including all the in-between times. So when we have that situation, we still have y equals a b to the x. But we are going to have to find the growth or decay factor. And if we know y values for 2 of the consecutive x values, we can find the rate of change. So I definitely want you to highlight r equals y2 minus y1 over y1.
It's so small.
And don't forget b equals 1 plus r. And that's for a discrete situation, so when we don't have the in-between values. All right, we're going to look at the Iberian Lynx. The table shows us 2 population samplings of the Iberian Lynx, in year 2003 and in year 2004. Our population decreased from 150 to 120. If this trend continues and the population is decreasing exponentially, how many Iberian Lynx will there be in 2014? So we're going to start out with y equals a b to the x, where b is 1 plus r. We need to make sure we identify what's x and what's y. Check this out. They didn't use 2003. We're not inputting the number of years since the birth of Christ. We are putting in the number of years since 2003. So 2004 will be year 1. 2005 would be year 2. So x is the number of years since 2003. And y is the population of the Iberian Lynx. So we're going to find r using this formula. We're going to go y2 minus y1, so it's 120 minus 150 divided by y1, divided by 150. So that gives us negative 0.2. So our r value is negative 0.2. We go 1 plus negative 0.2 and we get 0.8, which makes sense because if we're losing 20% of our population, we are left with 80%. So the amount will give us how many are left. So if we want to model that, we go y equals a, which is the starting amount, b to the x. We know that a is going to, even plugging in 0, we know that a is going to be 150. That's how much we have at year 0, which is 2003. So our equation is equal to y equals 150 times 0.8 to the x. We want to find out what the population is going to be in 2014. So we subtract 2014 from 2003 to see how many years since 2003, and we get 11. So we are going to multiply 150 times 0.8 to the 11. We do this calculation in our calculator and we get 13. So if 2003 to 2004 trend continues, there will be 13 Iberian Lynx in the wild in 2014. I'm going to give you guys a moment to calculate what the population is going to be in 2020. For the video. So if you subtract 2020 minus 2003, you get 17. Plug 17 into the equation, chug that in your calculator. You can't have a partial lynx. So in 2020, there's approximately going to be 3 lynx.
Would not be as cute.